In this lecture, I would like to work through a few examples, in particular, work through a few of the homework 5, assignment 5 problems for you. In the previous lecture, we learned that the order in which we need to go about tackling dynamics problems is first of all identify your object, know what your object is, and go ahead and identify all the forces acting on the object. We covered this in chapter 4. Having done so, draw the free body diagram for the object. In the free body diagram, you choose if you're talking about motion on a plane or a linear motion, then you choose the appropriate xy Cartesian coordinate system. The object, of course, is considered at the origin, and then you draw all the forces that you've identified, like weight, normal force, let's say here's F pull, and some kind of a friction force working in the reverse direction to motion if motion is towards the positive of the x-axis. Now, in drawing the coordinate system, it's probably a good idea to choose the positive x in the direction of motion. So if you have a box on a slope sliding down, it's probably best to go ahead and draw your x-axis slanted downwards along the motion of the box. Then your y will be like this, and of course your weight vector would now act directly down. This is a W there. Normal vector along the y, friction backwards, and that's about it in this case. So it's probably, as I said, a good idea to choose the positive of the x-axis to be along the direction of the motion. That way, if you end up with a positive velocity, you know the object is moving forwards. If you have a positive acceleration, the object is speeding up, etc. Now, having done your free body diagram, the next step is to do vector algebra on all the forces that you've identified and drawn on your free body diagram to figure out the net force, the sum of all the forces. And the sum of all the forces gives you acceleration, because Newton's second law states that acceleration is net force divided by mass of the object. Now, do bear in mind that this is a vector equation, which means that if you're dealing with the xy coordinates, then acceleration along x is given by the net force along x direction divided by mass, and the acceleration along the y direction is given by net force along the y axis divided by mass. So depending on what coordinate system you're working with, you need to decompose or do your analysis, the net force divided by mass analysis on each axis. Having obtained ax and ay, now you can combine these vectorially, of course, to get the acceleration vector. Or if you need to, prior to doing this combination, if you need to use any of the kinematic equations, then you go ahead and use, for example, acceleration along the x-axis to figure out the velocity along the x-axis final. If you know velocity of the x-axis initial plus ax delta t, etc. Similarly, velocity along y final is velocity along y initial plus ay delta t. So you use the kinematic equations after, in the last step, having figured out the acceleration, of course, using Newton's second law, which you apply having developed your free body diagram after you identify the forces. So please remember to tackle the problem in this order: identifying forces, drawing free body diagram, figuring out the net force, and then using the kinematic equations. Now let's start with a few simple examples. Let's say that we are interested in finding this example is actually in the book. So let's say we are interested in figuring out the velocity of a car which is being towed by a rope after 5 seconds. So here's a motion diagram for the car. The car starts at rest and speeds up under the net force acting on the car. The car is our object. We've identified tension because there's a rope attached to the car which is pulling it. There's normal force because the car is in contact with the road. Friction force because the car is moving to the right. And of course weight, our long range force. So doing a free body diagram, we've once again chosen our x-axis to be in the direction of motion. Weight is pointing directly down, normal force directly up. Tension in this case is along positive x, and friction is opposite to that of motion. Now we're told that the car weighs 1500 kilograms and that the tension in the rope is 2500 newtons and that the friction forces sum up to 200 newtons. So and we also know that at time t equals 0 seconds, we are at x equals 0 meters and our velocity is 0 meters per second, i.e. the car starts from rest. So having given this information, what is the velocity at t equals 5 seconds? Well, from our free body diagram, we apply Newton's second law, which says that sum of the forces along the x direction equals mass times acceleration along the x direction. What is the sum of the forces along the x direction? Well, we only have two forces along the x direction. There's tension and there's friction force. So T, positive T, because it's pointing towards the positive of the axis, minus F. And based on the numeric values given here, that is equal to 2300 newtons. Therefore, our acceleration is 2300 newtons divided by the mass of the car, which gives us 1.53 meters per second squared. Having obtained acceleration, now we can go ahead and apply the kinematic equation that we have for calculating the final velocity given the initial velocity and delta t, and we end up with the final with the answer that we are after, which is 7.65 meters per second. Simple example. Just a reminder that on friction, what we discussed in the last lecture, the friction comes in, the types of friction that we're going to be dealing with mainly is either static friction or kinetic friction. Kinetic friction is when the object is in motion with respect to a surface, and kinetic friction has a constant value, Fk, which is given by normal force times the coefficient of kinetic friction. And static friction is when the object is, of course, not moving, is at rest with respect to the surface that it's in touch with, and it does not have a constant value. The value of the static friction, Fs, depends on how hard one pushes on the object. However, the maximum value, Fs max, is equal to normal force times coefficient of static friction. Fs max is the value where the object slips, starts to slip. So any value above Fs max would get the object accelerating. Just a recap on what we covered the last lecture. So let's now do an example involving friction. Let's say we have here we have a load sitting at the back of a truck, and the question is excuse me, the question is, what is the maximum angle theta that the truck bed can be tilted to without the load slipping down the truck. So the load here, the chest of drawers, is our object. The forces acting, of course, our weight, the long range force. There's normal force because it's in touch with the truck bed, and of course static friction force. We're interested in the the load is actually is at rest with respect to the truck bed here. So now let's go ahead and do our free body diagram. Once again, if the load were to move, it would move down the slope, therefore we choose our x-axis pointing down, and here is angle theta, the maximum angle we're interested in figuring out, the tilt angle. Now, as far as the forces go, W, this is W, points straight down, normal force pointing along the y-axis, and static friction force is towards the negative of the x-axis, the direction opposite to the would-be motion. Now, let's now apply Newton's second law along the x-axis. And Newton's second law along the x-axis states that sum of the forces along the x-axis must equal mass times acceleration along the x-axis, and if acceleration is 0, as it is in this case, of course that means the sum of the forces must equal 0. What are the sum of the forces along the x-axis? Well, it's the minus Fs is the friction force that we have, and W sine theta is the x component of weight. And if you look at this triangle there, you see that Wx is equal to W sine theta. So W sine theta minus Fs must equal 0, which gives us sine theta is equal to Fs max. Here we are interested in Fs max, of course, the maximum angle. The maximum angle that we are interested in is when static friction force is maximum. So sine of theta max is Fs max divided by weight from this equation right there. But we still can't solve this equation because we don't know what the maximum static friction force is. To solve that, we need to look at the y-axis and apply Newton's second law. Here we have sum of the force along y must equal may, which is in this case 0 because there's no motion along the y-axis, and the forces along the y-axis are normal force, here it is, and the y component of weight, wy, which is minus W cosine theta, by looking at this green triangle in the free body diagram. So n minus W cosine theta must equal 0, which gives us normal force is equal to W cosine theta. Now that we've established a expression for normal force, we can use the fact that Fs max is given by normal force times coefficient of static friction, and coefficient of static friction is given to us in this problem, which means that maximum static friction force is equal to mu s W cosine theta. Now if you go ahead and substitute this expression for Fs max in this equation, we end up with what we have down here, i.e. sine of theta is mu s W cosine theta divided by W. Notice that w is cancelled, and we end up with sine theta over cos theta, which is tan theta equaling mu s, or in other words, theta is inverse tan of mu s. So in fact, to solve this problem, we did not need to know mass of the object nor kinetic friction coefficient, whatever. So we could go ahead and find the maximum angle by doing this simple analysis. Another reminder about the drag or air resistance, and we said that air resistance is another friction type force which is always directed in opposite to the direction of motion. In this case, direction of motion is forward in the positive x direction, and its magnitude is given or is approximated by this relationship, which is 1/4 of the cross section. A is the cross section of the object times velocity squared. And we also in the last lecture showed that if an object falls, is in free fall, then in the absence of air resistance, of course, its velocity will follow a curve, a straight line like this, where the slope of the line is minus g, of course, dv dt. This is dv dt is minus g. It's an object in free fall. But as velocity, if there is air resistance, as the velocity increases, the magnitude of drag increases, which means that there will reach a time when drag equals weight in magnitude, but of course they are pointing in opposite directions, which means that the net force in the y direction on the object becomes 0, which leads to acceleration in the y direction becoming 0. That means that the slope of the line, there will reach a time when the slope of the line, this is our dv dt, will equal 0, and that value is called the terminal velocity for the object. So just a quick recap. Now let's take a look at a few of the homework problems for assignment 5. We have a ring which is tied with 2 ropes which are at 90 degrees to each other, and there's a third rope with a tension of 100 newtons pulling at an angle of 30 degrees as shown in the diagram, and we're asked to find T1 and T2. Well, identifying the forces is simple in this case. We have T1 and T2 as shown here in the diagram. Now we go ahead and do our free body diagram. Free body diagram, I've marked T1, T2, and of course T, the value for which we know. Now apply Newton's second law along the y-axis and along the x-axis. Along the y-axis, the sum of the forces must equal 0 since nothing's moving, so AY is 0, since AY is 0. And if you look at the y-axis, we have 2 forces. There's T2, and there is the y component of T, which is minus T sine 30 degrees. That must equal 0, which means that T2 is equal to T sine 30 degrees, and we know what T is and what the angle is, therefore T2 is 50 newtons. So we got T2. To get T1, you do the same analysis, but now along the x-axis. Along the x-axis we have minus T1, and the x component of T, this is Tx, so this was Ty, and x component of Tx is T cosine 30, which gives us T1 equal to T cosine of 30 degrees, so whatever the numeric value is, you can figure out. Let's do an example here. We have Plot of velocity versus time for an object that has a mass of 2 kilograms, and we are asked to find the force acting on the object at t equals 1 second. So this is at t equals 1 second. So we're interested in the force acting at the object at t equals 1 second, t equals 4 seconds, and t equals 7 seconds. Well, as Newton's second law states that the force acting on an object is equal to mass of the object times acceleration of the object. So if only we knew the acceleration at these times, then we can go ahead and figure out what the force is by multiplying it by the mass which we're given. Well, acceleration is dv dt, so what we need to do is figure out the slope of the line at those points. At t equals 1 second, we're dealing with a straight line, so figuring out the slope is a simple matter, rise over run, which gives us a slope of 4 meters per second squared, which means that the force acting on the object is 8 newtons. At 4 seconds we have another straight line with 0 gradient, which means that the force is equal to 0 newtons. And at t equals 7 seconds we have a negative slope of minus 6 meters per second squared, which results in a force of negative 12 newtons acting on the body. Now, in this scenario, as the reverse of what we just went through, we are given force acting on an object which has a mass of 2 kilograms, and we're told that at time equals 0 seconds, the position of the object it is 0 meters, and the object starts at rest 0 meters per second. The force versus time is shown in this graph here, and we are asked to figure out what the velocity of the object is after 6 seconds, i.e. the velocity at 6 seconds here. Well, to figure out velocity at 6 seconds, we know that velocity at 6 seconds is equal to velocity at 0 seconds plus the change in velocity delta v from 0 seconds to 6 seconds. Well, change in velocity delta v from 0 seconds to 6 seconds is the integral from 0 seconds to 6 seconds of acceleration dt, or the area under the curve from 0 seconds, area under the acceleration versus time curve from 0 seconds to 6 seconds. We are given the force versus time curve, so what you need to do is convert this curve to an acceleration versus time curve, and that's a simple matter to do. The shape of the curve remains the same, the time scale remains the same. All you will need to do is apply Newton's law, which says if you divide force by mass, then you get acceleration. So 4 divided by 2 gives us 2 here, and minus 2 divided by 2 gives us a minus 1 there. So it's a very simple matter to do this conversion. Having done that, next step is to figure out the area underneath the curve, or the integral from 0 seconds to 6 seconds. So that's this area here plus this area there, and if you do the sum you end up with 4 meters per second for the area, as the calculations here indicate. So now that's the change in velocity from 0 seconds to 6 seconds, but since the object started at rest, as the problem stated, that means that the velocity at 6 seconds is 4 meters per second, of course. Now, had the problem stated that this is, well, actually the problem does state that this is a force acting along the x-axis, fx. Let me raise this. So this is a force, so this is a force acting along the x-axis, therefore the velocity that you figure out is actually vx. Okay, we just figured out vx. But the problem stated that there's also another force, Fy, which is identical in shape and magnitude, but acts along the y-axis on the object. Then, of course, following the same analysis, you would have ended up with Vy at t equals 6 seconds is equal to 4 meters per second. Alright, so now the problem asks you what is the final velocity of the object. Well, do remember that if you, this is our x-axis, this is our y-axis, if you just figured out that Vx is, this is our Vx, that's 4 meters per second, and this is our Vy, that's also 4 meters per second, then velocity v is given by the Pythagorean theorem, which is Vx squared plus Vy squared. So you need to do a vector addition of the two to get velocity v. And in this case, this would be a square root of 32 meters per second for the magnitude of v, and as for the directional v, to find angle theta with respect to x-axis, well, theta is equal to inverse tan. We've covered all this in chapter 1 or 2, I don't remember which chapter, but way back. Tan to the minus 1 of Vy divided by Vx. So the velocity, the final velocity of the object, had there been two forces, Fx and Fy, as given in the diagrams that we just had, then the velocity of the object at 6 seconds would be given by a magnitude of square root of 32 meters per second, and in a direction given by this tan to the minus 1 of 4 divided by 4, which is 1, which is in fact this is a 45-degree angle. Okay, I believe this is one of your homework problems. So we have two ropes supporting a beam. The beam has a 1000 kilogram mass. The two ropes can support a maximum tension of 6000 newtons. That doesn't mean that the tension is 6000 newtons in the ropes. That's a common mistakes that students make in tackling this problem. That's why I want to go through it. That's the maximum tension that the rope can support before breaking. What we need to figure out is the tension in each rope. Well, in the drawing I've identified the forces W, T1 and T2, and then on the right hand side we have the free body diagram, which shows W, T1 and T2 with the respective angles. Now apply Newton's law along the y-axis and along the x-axis, and you should end up with the expressions given. So I'll let you take a look at those expressions. They're self-evident. So from these expressions you can now come up with an expression for T2 in terms of T1 by doing some algebraic maneuvers, and then go ahead and, so this is a pair of simultaneous equations basically that you need to solve. So now you can go ahead and solve for both T1 and T2, of course. So I'll let you go through the algebra yourself. That's a trivial matter. Now, weight and apparent weight. The expression that we developed in the last lecture for apparent weight, just a reminder once again, everything I'm going through in this lecture is what we covered in the previous lecture, but this is once again another homework problem, so I'm kind of giving you hints on how to go about solving these homework problems, which is I guess due next week. So apparent weight is given by this expression, mass in times acceleration due to gravity plus any acceleration that the object has along the y-axis, and of course we know that weight is mg. Now, in the elevator problem in your homework, we are given the apparent weight versus time for a person, and we need to figure out the displacement along the y-axis over the 12 seconds. So that's what we need to figure out, but we don't know the mass of the person. But studying the apparent weight versus time curve, you see that the person's apparent weight is a low number for starters, then it becomes 750 newtons for a good 8 seconds, and then it increases up for 2 seconds before coming back to 750. This is a person riding in an elevator, so let us come up with a physical reason why we have such a curve. Well, obviously the elevator needs to, we get an elevator, what's the first thing we do? We press the button for a floor, either up or down. Then the elevator accelerates either up or down until it reaches, let's call it a cruising speed, and then it continues at that cruising speed till we get close to our floor, where the elevator now applies the reverse acceleration to either stop it, well, to stop the motion, such that we can get off our floor. So obviously in this middle region, that's the cruising region for the elevator, where acceleration in the y direction is 0. It's moving at a constant velocity. So this must be our weight, right? That's mg. So from this information we can go ahead and figure out what the mass of the person is. And are we moving up or down? Well, by looking at this diagram, we are actually moving down, because when the elevator first starts, this green region here, our apparent weight is lower than our weight. That's 600 newtons versus 750 newtons, so which means that there's an acceleration, a negative acceleration downwards. And after we come down close to the floor that we're trying to get off, the elevator applies a positive acceleration to bring the elevator to a stop. So our apparent weight now rises from 750 to 900 newtons. So by having established this, then go ahead and apply this equation so that you can figure out AY for both 0 to 2 over the 0 to 2 seconds, and also the 10 to 12 second region, and you should end up with this plot down here, where the acceleration is negative 2 meters per second for starters, and then it becomes 0, so this is acceleration of 0, y, the elevator is cruising, and then there's a positive acceleration in this region to bring the elevators to a stop. So this is a negative acceleration down here, and a positive acceleration from 10 to 12 seconds. And next, well, the question is after how much vertical displacement do we go through. Well, you need to remember that this displacement is an integral of velocity with respect to time. So it's the area under the velocity curve. So to figure out displacement, you need to generate the velocity curve from this acceleration curve. Well, for the t equals 0 seconds, we start at rest, and then we have an acceleration of negative 2 meters per second squared, which means that in 2 seconds we reach a value of minus 4 meters per second. We continue at that velocity for the next 8 seconds rather, and then there's an acceleration of positive 2 meters per second squared, bringing the elevator to a stop from 10 seconds to 12 seconds. So the area underneath this curve is now the area of this triangle plus the area of this triangle plus the area of this rectangle. If you add everything up, you should end up with minus 40 meters as our displacement. Alright, I'll give you a peek of how to go about solving this problem, but I won't go through this, but you can study it on your own. It's one of your homework problems, so it's a good problem to go ahead and do. Just remember the most important thing to remember here is that the tension in a rope, a string, is constant throughout. It doesn't matter how the rope meanders through, it's the same value. So that's the most important thing to remember. To figure out the tension, what you do is you look at one end of the string where we know the tension must equal the weight, force due to gravity or weight of the 6 kilogram box, or weight rather. And then, as I said, it's do your free body diagram and your F equals ma analysis along the x and the y axes to get the answer that the problem is seeking. Okay, this is yet another one of the homework problems, and I'll let you take a peek at it here. The most important thing, of course, is identifying all the forces acting on the body. F push is given, but we also have weight, there's normal force, and friction force. The box, we're told, is sliding down. So if it's sliding down and friction force is upwards, then you generate your free body diagram as shown, and once again do your analysis along the x. Now along the x-axis, the sum of the forces must equal 0 because there is no motion, there is no acceleration along the x-axis. And along the y-axis, we are told the box is sliding down at constant velocities, which means that acceleration along the y must also equal 0, i.e. net force must equal 0. So you go about doing your analysis. That is an equilibrium problem, and you can figure out what force the problem is after. Okay, that's all I wanted to share with you as far as the giving you hints on how to go about solving the problems for assignment 5.